it is not easy to follow the units in this one. I mean, the more I work on it, it keeps changing here and there, and yeah, that's the nature of it. Now, laboratory to field correction. We call it laboratory to field correction. So when you have beam fatigue data, and in the field, it's really not a beam fatigue test. Field, it's different. It's, you know, linear system, they're all glued together. There's confinement effect, depth effect, this effect, that effect. So what they did is they come up with a correction factor for that equation, and for the depth, based on depth, for bottom-up and top-down cracking. And also they made a correlation between beam fatigue test and air voids and effective binder content by volume. So the test that you run in the lab, it might be different than in the field. So they came up with two factors, and they added this to an equation, the C and CH. CH is the factor really converting a lab type testing data to field testing data. Again, this is at material level. And C is like volumetrics, based like a correction based on the volumetrics. So if you're expecting different volumetrics than what you've tested in the lab, then that's that's what you get here. The fact that VBE and VA are here makes a huge difference. So the reason why VBE and VA is so significant input is because of this. Notice 10 to the power 4.84, 10 to the power. And that directly is multiplied by this NF equation to get your new NF. So the NF is affected significantly by effective binder content that's used here and also here. For top-down cracking, it's here. For bottom-up cracking, here. Unfortunately, that's one of the issues with PMNME. It doesn't distinguish between them in a material level. So that is a deficiency for the top-down cracking. So top-down cracking model PMNME is a bit, you know, funky. It's not. Yeah, no, you know, I'm not surprised. So, but bottom-up cracking is the one that is pretty accurate. Actually, it's very good. Bottom-up cracking, fatigue cracking formulations in PMNME is very, very good. Rutting. How often the payments fail from rutting in Michigan?
Almost, I would say very, very, very few.
Okay.
Sometimes, occasionally will happen. And then in reality and in the modeling, it's reflected. We usually have problems with the fatigue cracking, bottom-up cracking. It's what we designed to.
Mm-hmm. That makes sense. Yeah, makes sense. Okay. Now, this is the table that shows the different bottom-up cracking and top-down cracking final material damage models. These are the beta 1, beta 2, and beta 3 are the calibration factors. C and CH are the correction factors. And here for bottom-up cracking, we use the tensile strain at the bottom of the pavement. That's what we use in our morning exercise today. We looked at the bottom. For top-down cracking, we look at the tensile strain on the top near the tire. So here near the tire, there is the maximum. Usually the stress is radial strain is compressive here and then becomes tensile and then becomes zero later on. So when the tensile strain at the edge is, that's the one that is used in top-down cracking formulation.
I'm sorry, the E in those correction formulas again is the error between calculated and measured.
Which one?
The E in those things.
Here?
No, the previous one, I'm sorry. The E in those correction calculations.
This one?
Yeah.
No, this is exponent to the power.
Oh,
or exponential. So it's exponential to the power.
Okay, yeah. What is the input into that?
Height of the AC. So if whatever the height of the AC is, you enter here, you got a CH value directly, and that's your correction factor that goes into here. NF equation. Okay. All right. So those are, so once you calibrate this, these are the numbers that you need to change. So as I said, for bottom-up cracking, tensile strain at the bottom goes here, and the modulus of the bottom goes here. For top-down cracking, the tensile strain on the surface and the strain on the surface is used here. And unfortunately, if you look at here, one set of coefficients are used for both top-down and bottom-up cracking. So when you can't really change beta 1 and beta 2 for bottom-up and top-down cracking. So you have to choose one of them. You don't have two. So you have to be choosing one of them to be accurate. And most people choose the bottom-up cracking and not the top-down cracking. So that's a deficiency. All right, so I was going to repeat the exercise that we've done by adding the C to the NF equation right here. Okay, so you're all ready? Very quickly, let's go to the Excel sheet that we had. So in the morning, we used an Excel sheet. Did I put that Excel sheet here? But I'll put that in here really quickly. All right. Okay. Okay, so we were working on this sheet in the morning. So I hope you still have this sheet with you. So we ran structure A and B, and we said NF, A is better than B for this modulus combination, and then B is better than A for this modulus combination. So what I'd like to do here is let's add this C without doing this correction for CH. Let's just add this C to this. So I'm going to copy and paste here. Not here. Here. Let's see. This is the C. Everybody has this sheet open? Yes? Okay. So what I will do is I'm going to, let's do this. Let's wrap text. So I'm going to have a corrected NF here. Corrected NF here. NF corrected. So based on VA and VB. So let's say air voids, let's have the same for all of them. 7% air voids for all of them, all conditions. And let's say 11 or 10.6 for all conditions. This is the VB, effective binder content by volume. This is the air voids by volume.
So that's as constructed air voids.
Yes, as constructed air voids, and this is the as constructed effective binder content by volume. So all I do is first I'm going to come up with a C. Let's just go here to the right a little bit. Let's come up with C. C is equal to 10 to the power 4.84 times parenthesis VB divided by parenthesis VB plus VA minus 0.69. Okay. Are you all with me here? Okay. So correction factor 0.37 for all of them, and essentially equals NF, whatever the NF we had, multiplied by this. It's the same equation essentially. So 1 million all of a sudden went down to 449,000. So we have corrected NF. Okay, so if you look at this, conclusions will not change. Still, A is still better. So I'm going to change all this color to a different color. Still this way. Okay, so A is still better, and here let's merge these two and merge these two. Okay, so A is still better than B here, and here B is still better than A. How can I make B better? If I change air voids to 8, becomes 313, 8.5. So if I move my air voids from 7 to 8.5%, this is not a big difference. 7%, in the field, you don't get very big accuracy in air voids, 7, 8.5, all over the place. Am I correct, Dan, or not? Dan?
I'm sorry, what?
Air voids in the field, when you do the construction,
Yeah.
air voids are all over the place. 7, and
It depends, but it varies, no doubt.
3.
I got 4 for the C value for the first one.
So let's look at here. This one. Let me look at your cells.
Oh, you changed 10.6. Oh, you always had it at 10.6.
Yeah, 10.6. Yeah, you got 30.6.
Hey, that's what I got.
Is that the right number? Okay. You can see when you go from 7 to 8.5.
Multiply the two.
Yeah, just multiply with the, or we had an original NF, we have corrected NF. Okay. So you can see changes in air voids significantly affect the results. Let's go back to 7 again, and I'm going to change VB effective from 10.6 to let's say 9.5. So it's a little less effective, but we don't get to not much less than 9.5, or let's say 9. Yeah, so if the effective binder content goes down to 9 by volume, then B becomes all of a sudden better than A. So point of all this exercise is that air voids and effective binder content by volume are very significant inputs for fatigue cracking. And this is why. Is this clear? No? Yes.
Can you put it on column R again?
The effect of air voids and binder effective is very significant on NF calculations. What's that?
Could you put it on column R again, the C? I had something wrong.
Okay. So it's 10 to the power. I'm trying to implement this one. 10 to the power 4.84.
Just gonna type it over again. 10 to the
Okay.
power.
Okay.
Got it.
Perfect.
Thank you.
All right. So